Step 6, profiling segments. For characterizing segments, it's also important to assess the segmentation solution and to see how close are segments to each other, how can these be differentiated from each other using projections. So first we want to look at this using artificial data. So we set a random seeds. We're all generating the same artificial data. We're using the function price feature for generating the artificial data. Will use a sample size of 500 for both, like a dataset following a 3-cluster distribution, and the other is a dataset which is formed as an ellipsoid. For both, we're using k-means clustering to construct a 3-cluster solution. We're using step CC-clus, which means by default the k-means algorithm is used with 3 random initializations and the best solution is stored. So we see the progress, the running of the 3 random initializations here with the 3 stars. And if we want to look at what does this solution look like that we obtained, we can just plot the object which is returned. What we want to do is now we want to construct one figure which contains 4 plots, and to put all those 4 plots on one graphic device we use par. So we're setting the parameters for a graphic window using mfrow equals to 2, which means we want to have 2 rows and 2 columns. We're saving the old settings here so we can adjust our parameter settings afterwards once we have finished our 4 plots. So these 4 plots will go into the same graphic window. We are using the default plots for 2-cluster solutions, and then we are modifying these default plots because by default they contain the data points themselves. Points equals false means the data points are not plotted, and these plots also contain cluster hulls, and this here can we specify arguments for these cluster hulls. How should be the inner 50% hull shaded? That's the information given here. So let's have a look. Let's generate that plot and see what it looks like. So this is here we have the same cluster solution plotted twice, once with the data points and once without the data points, but the cluster hulls here, that's the argument how much should it be shaded in here. This kind of graph is called a neighborhood graph, and it plots here the nodes 1, 2, 3 are correspond to the centroids of our 3 clusters, and the edges between our nodes, they represent closeness between clusters or centroids. Given that there's no edge between cluster 1 and cluster 3, that indicates that none of the observations here in cluster 3 and none of the observations here in cluster 1 have the other one as the closest centroid. So it's always cluster 2 which is closest to them. And we see here, this is in both plots, the dashed line, that's the convex hull. So all data points which are assigned to this cluster are within that hull. And then we have the solid line, which means this contains 50% of our of the observations assigned to this cluster. So this allows us to see how are our clusters shaped, and we can also see how separate are these clusters. Compared to the data which follows an ellipsoid shape, we see that the neighborhood graph, the centers, and the edges in between, they look rather similar. But if we look at the cluster hulls, we can see the difference to the 3-cluster solution in the sense that they are very close and there are no gaps in between. This is the result for artificial data. We're resetting our parameter settings. But if we have real data like our vacation motive dataset, the problem there is if we want to look at a 6-cluster solution, we cannot plot the 20-dimensional data directly. We need to project it into a 2-dimensional space to be able to do so. We could just select 2 variables and plot what do the vacation motif clusters look like there, or the alternative is to use as a projection principal component analysis. And this is what we're doing here. We're performing a principal component analysis on the dataset, and then we plot the object containing the 6 cluster solution by projecting into that PCA space, and we're plotting the second and the third dimension of the PCA space. So we're plotting the second principal component and the third principal component. So that's the exactly same thing. We have our neighborhood graph. So we have the 6 nodes correspond to the 6 centers. We have edges in between which indicate sort of closeness. And keep in mind that these edges represent the closeness in the 20-dimensional space, whereas here we only see a projection into 2-dimensional space, which might be misleading. So centroids could look close in the projection, but are far away in some other dimension, which we don't see here. And we can also add the projection axis to be able to see how the variables can be used to identify the principal components. So this just adds this. Overall, this seems rather cluttered. We could try to simplify the plot and avoid plotting all 1,000 observation points we have. So we set points equals false. We use lighter colors, and the hull arguments again for the density of the inner 50% is used. Otherwise, we're using the same thing, and we're again adding projection axis, this time in a different color. We want to use dark blue, and we make them a bit bigger with the 6 here. So then we can zoom in. One can, for example, see here the cluster 3 and 6 are pretty separate in that projection, and we could also see, is there a connection between the two, yes or no? But overall, so principal component 2 allows us to differentiate between cluster 3 and 6, but for example not between cluster 3 and 5, which doesn't mean that there couldn't be a separation between the two in another dimension.